have already suggested that weather systems are driven by the movement of energy. Now we will look at the source of that heat energy, the sun's radiation, and the distribution of heat in the atmosphere. We will discover that the sun heats the earth and the earth in turn heats the atmosphere. We also identify water vapor as the most important heat transfer mechanism in the atmosphere. Heat and temperature. Temperature is a measure of the level of molecular activity within a substance, and it is not a direct measure of the amount of heat energy present. You can have very hot small objects that contain little heat energy and large warm objects that contain huge amounts of heat energy. We have to make a clear distinction between heat energy and temperature. When an object is cooled to a temperature of absolute zero, minus 273 degrees Celsius or 0 Kelvin, all molecular activity ceases and the object contains no heat energy. If we add heat energy, the temperature will go up. How much the temperature goes up depends on the material we are heating. We define the units of heat energy by reference to behavior of water. We say that the amount of heat needed to raise 1 gram of water by 1 degree centigrade or 1 Kelvin, as they are the same size, shall be called 1 calorie or cal. Thus, if you add 10 cal to 1 gram of water, the temperature will rise by 10 degrees Celsius, or if you add 10 cal to 100 grams of water, the temperature will rise by 0.1 degrees Celsius. Water has the highest ability of all common substances to absorb heat in this way, so most other materials will heat up more easily. The ratio of the amounts of heat required for the same temperature rise is called the specific heat of the substance. Water has a specific heat of 1.0, but most other common substances have specific heat values of much less than 1.0. For example, ice. Ice has a specific heat of 0.5 and rock a specific heat of 0.25, depending on its composition. This means that it takes 1 calorie to raise the temperature of 1 gram of water through 1 degree Celsius. It takes a half of a calorie to raise the temperature of 1 gram of ice through 1 degree Celsius and only a quarter of a calorie to raise the temperature of 1 gram of rock through 1 degree Celsius. This fundamentally affects the way oceans and land masses respond to the energy input from the sun. For the sea stays at more or less constant temperature while day and night, winter and summer, the land heats up quickly and cools down quickly. Latent heat. Energy is also needed to loosen the bonds that hold molecules together and so change solids to liquids and liquids to gases, referred to as change of state of aggregation. Inside the system ready to be released to the surroundings when a change of state in the reverse direction occurs. To change a gram of ice at 0 degrees Celsius to water at 0 degrees Celsius, you have to add 80 calories. There will be no rise in temperature, just a change of state. To make the change from liquid water to water vapor at 100 degrees Celsius, you have to add 540 calories per gram. Going the other way, 1 gram of water vapor condensing into water releases 540 calories to the surrounding air, and 1 gram of water freezing to ice releases 80 calories into the surrounding air. These heat quantities are called the latent heat of fusion, melting, solidification, or freezing, and the latent heat of evaporation, condensation. The amounts of heat energy involved in changes in the large-scale atmosphere are very significant. Here 1 gram of ice at minus 273 degrees Celsius is heated. To bring it up to 0 degrees Celsius, about 137 calories must be added. A further 80 cal is needed to change it to water at 0 degrees Celsius, bringing the total heat content to 217 cal. Another 100 cal brings the water to 100 degrees Celsius. But now a further 540 cal is needed to change the water to water vapor at 100 degrees, more than doubling the heat energy content of the system from 317 to 857 calories. If now the water vapor changes back to water, the heat content is more than halved, and 540 cal per gram of water is released to the surroundings. Of course, water can evaporate at temperatures below 100 degrees Celsius. It is just that the process is slower at lower temperatures. The principle is the same, but the calories needed to make the change are rather more at lower temperatures, reaching about 600 cal for temperatures around 0 degrees Celsius. Note that water vapor can go straight to ice and ice to water vapor without passing through the water stage. The common term for this transition is sublimation. Sublimation will only occur if there is something present for the ice crystals to form on, either vegetation, existing ice crystals, or even very small particles of atmospheric dust known as sublimation nuclei. The latent heat value will be the sum of the two normal stages, about 680 cal. The energy released by changes of state of aggregation is extraordinary. Over the Amazon basin on a typical day, rising moist air forms convective cloud aloft and heavy rain falls. The latent heat of condensation released is enough to raise the mean temperature of the troposphere overhead by 10 degrees Celsius. This process of evaporation and condensation is one of the more powerful factors involving in the global movement of heat energy. Note, a change of state releases or absorbs energy. Insolation. Insolation is a measure of solar radiation energy received on a given surface area in a given time. The sun radiates energy at wavelengths around 1 micron, which changes from atomic radiation through ultraviolet and the visual spectrum to infrared. Fortunately for us, a lot of this energy is diverted, scattered and reflected high in the atmosphere, and much of the ultraviolet is absorbed in the ozone layer. From the tropopause down, about 15% of what is left is either scattered or absorbed in clouds, gases, and dust in the troposphere. Much still gets through, and is generally true to say that the sun's radiation passes through the troposphere to heat the Earth, and the Earth then heats the troposphere. The intensity of radiant energy from the sun that hits the Earth depends on its angle of arrival. The angle of arrival at any point is dependent on its latitude, the season, and the Earth's axis tilts in relation to the sun and the time of day. Here the radiation, which arrives in parallel lines from the sun, has the same intensity at A, B and C. But A and C have to cover much more surface around on the Earth, so the intensity of radiation falling on the surface is much lower. The extra distance that radiation at A and C has to pass through the atmosphere also slightly reduces the intensity on the surface. When the radiation arrives at the Earth's surface, some is absorbed and some is reflected back out to the troposphere and to space. How much is absorbed and how much reflected depends primarily on the type of surface. Forests, bluffed land, for example, absorb radiation energy readily, but snow and desert sand reflect it back. Oceans absorb radiation that arrives at high angles of incidence, as in the tropics, but reflect more when the angle of arrival is low. This is also true to some degree of all surface types. So, overall, we can say that the percentage of incident radiation energy that is absorbed by the Earth depends on the type of surface and the angle of arrival of the radiation. When the Earth absorbs the radiant energy from the Sun, its temperature rises. For any given quantity of heat energy that is absorbed by the Earth's surface, the rise in temperature will depend on the specific heat of the surface material. Water with a specific heat of 1.0 will show the lowest temperature rise, damp earth at greater rise, and materials like rock and concrete in cities the greatest rise in temperature. This is why in the sunshine the flagstones at the side of a swimming pool burn your feet when the water in the pool is cold. In the oceans the temperature rise is further limited by the deep penetration of the radiation and by circulation of the water, which mixes surface water with great stable mass of cold deep water. Note: the sea temperature is stable, land heats and cools. Because the degree to which the Earth heats the troposphere depends on the temperature of the Earth's surface, this is one of the fundamental factors in determining the behavior of the weather system. Remember, night and day, winter and summer, oceans maintain stable temperatures, while land masses rapidly heat up and cool down. The heating of the troposphere. The Earth has a much lower temperature than the Sun, and because of this radiates energy at much lower wavelengths, in the 10 micron band. Radiation at this wavelength is absorbed in water vapor and carbon dioxide, and by clouds, heating the troposphere, especially the lower troposphere, where clouds and water vapor are at a maximum. Some long-wave radiation is re-radiated and reflected back to the Earth at a maximum rate in overcast conditions. This is the first of the ways that the Earth heats the troposphere, by radiation. Note: the Sun heats the Earth by radiation. The Earth heats the atmosphere by radiation, conduction, and convection. At the surface in contact with the troposphere, an exchange of heat energy takes place by conduction. This can go either way. For if locally the surface is colder, heat will be taken from the air, and where the surface is the warmer, the layer of air in contact with the Earth will be heated. Conduction works by contact. The heat is conducted along the bar. Air is not a good conductor of heat. In the absence of any method for distributing the heat aloft, this effect would be confined to be a very shallow layer at low level, as indeed it is on very still days or nights. However, if the airflow in the lower troposphere is turbulent, it can transfer heat from the surface through the lower troposphere. This method is extracting heat from the Earth into the atmosphere is referred to as turbulence heating. The method for transfer of the heat aloft is convection, the vertical movement of air. This can be forced convection, air forced up over a range of mountains, or mechanical turbulence in the lee of hills or mountains. More usually it is thermal convection, where the heated air will have a lower density than its surroundings and therefore rises. Note: convection means the upward movement of air. The rising air carries energy aloft in two forms: ordinary heat energy, and latent energy. For as the air rises and cools, water vapor in the air may condense to form cloud, releasing its latent heat of condensation. These figures give you schematic diagrams of the complex interrelationship. Do not try to memorize the diagrams, they are only here to give you a general feel for the system. Note, the latent heat in water vapor transfers more energy than anything else. Long-wave radiation transfers out to the troposphere a large amount of heat, but a large amount is also re-radiated back to the surface. Out of all the energy transferred from the surface to the troposphere, not long-wave radiation accounts for only 42%. Warm air convection accounts for 12% and latent heat convection for 46%. Long-wave radiation out to space occurs from the upper troposphere, one reason why temperatures aloft are low. The final heat transfer method is advection, the horizontal movement of air or wind, because by definition advection only transfers energy horizontally. It is not responsible for heating the troposphere, only for redistributing the energy within it. We shall see later that advection has a substantial effect on the stability of air. Surface temperature. Having looked at the mechanism for the heating of the Earth, we would expect to find surface temperature varying widely by space, by day and by season. These figures show the world mean surface temperatures in January and July. Notice how, in January, the land masses in the northern hemisphere are extremely cold, while in the southern hemisphere they are hot. Note too the effects of cold sea currents off the west coast of Africa and South America, and of the warm sea currents in the North Atlantic and North Pacific Oceans. In July, the position has reversed. North America and Siberia have warmed up, Siberia reaching 20 degrees Celsius, while in the southern hemisphere the land masses have cooled down. There are very hot regions in Mexico, the Sahara, and on the Tibetan Plateau. The effects of the cold currents of Peru and South Africa can still be seen, but in the North Atlantic the sea temperature is about the same as the land temperature, and the contrast is very obvious. In the North Pacific, the sea temperature, remaining relatively constant, is now colder than the land temperature. The sea temperature of California has been more or less the same all year around. Sea currents play a major part in the distribution of heat at low level. So do the global winds. The warm winds blowing up over the Gulf Stream are moving heat horizontally by a process of advection. They carry heat in the same way that convection does, as warm air and as a latent heat. Warm, moist air drifting over cold surfaces and forming advection fog is carrying out the same process as convection and cloud formation, but horizontally instead of vertically. Diurnal variation of surface temperature. The daily or diurnal variation in surface temperature is also important, for on this depends the formation of radiation fog, for example land and sea breezes, and the development of convective cloud during the day. The balance between incoming and outgoing radiation is shown on this figure. For a typical day over land in May or September, in the middle latitudes, with sunrise at 060 local mean time and sunset at 1800 local mean time. You would expect the surface temperature to fall during the radiation deficit and to rise when radiation goes into surplus. This is roughly true. There are, however, more factors than just radiation at work. As the temperature rises, thermal convection begins, and winds can bring turbulent mixing of the air. Near the coast, sea breezes will bring the sea's stabilizing effect into play. Clouds, too, as we have seen, will give a blanket effect, limiting incoming radiation and reflecting back outgoing radiation, and therefore reducing the variation in temperature. Thick clouds are a more effective blanket than thin clouds. Note: minimum surface temperatures occur 30 minutes after sunrise and maximum temperatures at 2 or 3 hours after midday. The overall effect is that minimum surface temperatures occur at about 30 minutes after sunrise and maximum temperatures at 2 to 3 hours after midday, with the diurnal variation of surface temperature much reduced by cloud cover. This is summarized in this figure for clear skies and overcast conditions, and with the radiation pattern displayed for comparison.